We've made it to Unit 5, Matter-Energy Interface, the unit that is semi-confusing but ultimately eye-opening when it's fully understood. We learn about Einstein's revolutionary special theory of relativity. We combine the concepts about waves, photons, and matter to come up with the photoelectric effect. And lastly, we briefly covered radioactivity and the various elementary particles. For the final video in the series, let's go through each of these subunits and see how they apply to my life one last time. Formulated by Albert Einstein in 1905, the theory of relativity is the notion that the laws of physics are the same everywhere. The theory explains the behavior of objects in space and time, and it can be used to predict everything from the existence of black holes to light bending due to gravity to the behavior of the planet Mercury in its orbit. The theory is deceptively simple. First, there is no absolute frame of reference. Every time you measure an object's velocity or its momentum or how it experiences time, it's always in relation to something else. Second, the speed of light is the same no matter who measures it or how fast the person measuring it is going. Third, nothing can go faster than light. Having introduced his postulates and knowing that simultaneity of events is a relative concept, more sweeping conclusions were discovered. These include time dilation, length contraction, relativistic momentum, and even his famous mass-energy equivalence equation, E equals mc squared. Of course, these concepts are difficult to understand because they overturn our common-sense views of the world. However, let's still try our best to see how one of these concepts may be applicable in our lives. Remember the global positioning system we discussed back in Unit 1's video? Well, in order for our car GPS navigation system to function as accurately as it does, satellites have to take relativistic effects into account. Satellites fly around the Earth at a pretty quick speed, around 10,000 kilometers per hour. This may sound fast, but it's only about 1,000th the speed of light, so you might not think that it's fast enough for relativistic effects to take place. But even at a speed much slower than the speed of light, the satellite still experiences time dilation. It gets, quote-unquote, older by roughly 4 microseconds every single day. Include the effects of gravity, and this value goes up to about 7 microseconds per day. Though we can barely even blink in 7 microseconds, if this effect were unaccounted for, then our GPS would get us lost very, very quickly. After just a day, our location, according to the GPS, could be wrong to up about 8 kilometers. Fortunately, satellites are programmed to take these effects into consideration when planning our routes. For a different means of applying physics to our daily lives, rather than applying it to artificial technology, let's apply this physics to a natural phenomenon. In order for humans to breathe, we need oxygen. Now, for oxygen to be readily available, we need plants that convert our CO2 into O2. This process is photosynthesis. If you were in biology, this may not come as a surprise because you may have already been aware, but photosynthesis utilizes the photoelectric effect to cycle. Very simply, as Einstein worked out, the photoelectric effect just demonstrates that light can behave as a particle known as a photon. In photosynthesis, photons are absorbed by a plant, in which these photons then can go on to excite electrons to a higher energy level, allowing them to form chemical bonds to make glucose and the byproduct, oxygen. As can be seen in this diagram, in the P680 and P700 complexes, the absorption of a photon is crucial to continue the cycle. Therefore, it is evident that the concept of photons is of high significance in our natural world too. Finding our way to the last subtopic, radioactivity, is rather relevant in our lives. Everything we encounter on a day-to-day basis contains some sort of radioactive material, some naturally occurring and some man-made. In the air we breathe, the water we drink, the food we eat, the ground we walk on, and the consumer products we purchase and use. Although we might be familiar with the use of radiation in medicine, many people, when they hear the terms radioactive and radiation, tend to think of mutant-like figures. Careful analysis can identify and quantify the radioactive material in just about anything and show that radioactivity is more than its negative connotation. One life-saving application of radioactivity that I'm sure is in every one of your homes is the smoke detector. In its circuitry, contained is a low-activity americium-241 source. A tiny quantity of americium dioxide emits alpha particles, which ionize the air, making the air conductive and consequently permits a current to flow between the plates of the smoke detector. Smoke, however, will interfere with this ionizing process because smoke absorbs radiation, which reduces the current that flows. Therefore, any smoke particles that enter the unit will sound the alarm. Despite the fact that these devices save lives, the question, are smoke detectors safe, is still asked by those with an inordinate fear of radiation. The answer, of course, is yes, they are safe, but it is essential to read the instructions for proper installation, handling, and disposal. Now, I do believe some advancements can be made to our conventional smoke detectors, and this proposal I'm about to make has already been put into effect by some companies. With conventional smoke detectors, a predetermined threshold of smoke must be met to sound the alarm. Often, that threshold may be fooled by dust and steam, resulting in a false alarm. What's needed is multi-sensor detection, which requires the identification of multiple criteria before initiating an alarm. This could be sensor monitors for carbon monoxide, infrared, photoelectric, and thermal properties of combustion to ensure that there really is a danger before putting individuals into panic mode. The fact is, more people die from smoke than the actual fire, and no detection technology is perfect. The truth is that this advancement in smoke detection has proven to mitigate the loss of life and property, as well as provide detection in unique environments. This should be the new standard for smoke detectors from now on. That's it from me, but I hope that throughout the series you've taken away the immense impact physics has in our lives. Thanks for following along.